All right, welcome. So we're going to be doing a review today, just because we don't have time for in-class review again. What we're going to be doing specifically is we're going to start by just going over the exam that I actually gave my class last fall. I'll talk a little bit more like in more like general terms and stuff like that, because you're not going to get like the exact same exam, obviously. And then we're going to move on to the practice exam, which I posted as well. And so I always like to give the disclaimer that this is like not going to be like a super like not 100% comprehensive review or anything like that. So don't just limit your studying to just the information available or presented in like these two practice exams. Just kind of use these as a way to gauge like your level of understanding going into the exam, right? So if you only study these things, like there will probably be some gaps in your knowledge. So study your notes, your guided notes, read the textbook, practice more problems. These are just meant to give you some extra problems and stuff like that to work on, just to gauge your understanding overall. I'll talk. Let me like say like generally speaking about like difficulty. So last fall, I think I undershot with the difficulty of this exam. So probably this semester, like our exam 2 is going to be a little bit harder than the exam 2 that like I gave last fall, just by nature of that. So just kind of be aware of that like our exam is probably going to be a little bit harder than this one, just because the average of that exam was pretty high. All right, so verify that this is a linearly independent set. This is probably the first place where I probably made it a little bit too easy, because this is a very short problem. So all you have to do to verify something is a linearly independent set is compute the Wronskian of those functions. So the Wronskian, you just put the functions as your row in the or for the first row of the matrix, and then since there are only two functions, then we only need two rows. So the second row is just going to be the derivatives of those functions. I'm going to move this over a little bit and make some space, because then we're going to need to take the derivatives of e to the x cosine x and e to the x sine of x. How do I do that? We need to do a product rule. So this is e to the x times cosine x. So derivative of e to the x is itself. Leave cosine x the same. And then plus e to the x times the derivative of cosine, which is negative sine. So minus e to the x times sine of x. Same thing over here. Derivative of e to the x. Oh, come on. Redo. Oh my gosh. Okay. All right. Derivative of e to the x is itself. And then derivative of sine is cosine. So doing a little product rule there. All right. Now the determinant of this matrix is going to be this times this minus this times this. All right, so e to the x cosine times this whole thing. Remember that e to the x times e to the x is just e to the 2x, so I'm just going to distribute that to all that stuff, and then we'll have cosine x times sine of x plus e to the 2x times cosine squared of x. So that's this times this. Oh, by the way, I'm feeling a little bit sick today, so I apologize if I'm like sniffing and coughing and stuff like that. Hopefully it's not too distracting. All right, and now we subtract this times this. So that's going to be e to the 2x times sine x cosine x. So I'll just write it cosine times sine, just so it matches the other term in the beginning, because we're going to cancel those terms in a bit. And then e to the x times negative e to the x sine x. But this is going to be like a double negative, so it's minus the negative of e to the 2x times sine squared of x, because remember we're subtracting this times this, so both of these terms should be like flipped in sign. And then we notice that this and this cancel, and we're left with e to the 2x times cosine squared plus sine squared. And I'll factor out the e to the 2x. And then sine squared plus cosine squared is equal to 1, so this whole thing is equal to e to the 2x. And we know that e to the any power is never equal to 0, and therefore the Wronskian is non-zero, so we can conclude that this is a linearly independent set. Right. Careful not to stop too soon with this problem. Like if you were to like stop right here and then just say like, oh, this thing is not equal to 0, I would be taking some points off, because I would say it is not clear. Just looking at this term or this stuff up here, I would say it's not clear that this is a non-zero sum right here. I would even say that this right here is not necessarily clear that you understand why that is not equal to 0. Like I can look at this and I would know that this is non-zero, right? But I know that it's non-zero because I know that this identity is equal to 1. So basically what I'm trying to say is do as many simplifications as you possibly can to make it very clear to the reader or the grader or whoever that it has to be non-zero. Okay. Consider this differential equation. Let's find the complementary solution and then a particular solution, and then we will state the general solution at the end. Right, so this is a classic problem. This is like the whole like point of chapter 4 in my eyes. Is like this like big picture. This is like what chapter 4 is really trying to like teach us how to do. Is solve stuff like this. This is one of the like easier examples to be sure, but still, if you understand this, then like you probably understand like the big picture of like what we're doing in chapter 4. So to find the complementary solution, we're really trying to find when this thing is equal to 0, and so we take our left hand side, convert that to a polynomial, lambda squared minus 4 lambda plus 5. Set that equal to 0, and then you could either factor this or just use the quadratic formula. I don't know how to factor this without using the quadratic formula, so I'm just going to do that. So lambda is equal to negative b plus or minus square root of b squared minus 4ac all over 2a. It was pretty concerning on the last quiz how many people did not know how to use the quadratic formula. So I'm going to go over that right now because again, all right, this is your A, this is your B, this is your C, right? So the A term is is attached to the lambda squared term, the B term is attached to the lambda term, the C term is the constant term. So here our B is -4. So negative 4 becomes +4. Plus or minus the square root of b squared. B again is -4, so -4 squared is 16. And minus 4 times A is 1. And then times C, which is 5. This is all over 2A, 2 times 1. Okay. This is 4 plus or minus square root of 16 minus 20 all over 2. 4 plus or minus square root of -4 all over 2. So this is 4 plus or minus square root of 4 is 2. Square root of -4 is 2i. So this is I'm going to simplify to, well, 4 over 2 is just 2. And then plus or minus 2i over 2 is just I. All right, so what's our complementary solution? YC is equal to, well, okay, so what's our alpha, what's our beta here? So our beta is, so this is basically like 2 plus or minus 1i. So alpha is 2 and our beta is 1. So this is going to be C1 e to the 2x cosine of x plus, excuse me, plus C2 e to the 2x sine of x. Great. let's find a particular solution to the differential equation. So here, this is when we want to start by making a guess for the form of y sub p based off of what our right-hand side is. And so we have 2x plus 5 for our right-hand side. So we're going to guess that y sub p is also going to be linear, so ax plus b. And then we're going to plug this into our differential equation to solve for a and b. Give me 1 second. Sorry about that. Okay, so let's plug this into our differential equation. So yp prime is just going to be a, and so yp double prime is just going to be derivative constant is 0. Let's plug in. We get y double prime is 0 minus 4 times y prime, which is a, and then plus 5y, which is 5ax plus b. I'll distribute the 5, so it's plus 5b is equal to 2x plus 5. All right. Where's our constant terms? We got negative 4a plus 5b. It's going to be equal to 5. And then our x terms, we got 5ax is equal to 2x. So we get 5a is equal to 2. 5a is equal to 2. So a is 2/5. And then 5b minus 4a is equal to 5. I'll plug in our a value. 4 times 2/5. Oops. 4 times 2/5 is 8/5. It's equal to 5. Which is equal to, so 5 is going to be 25 over 5. And then we're going to add 8/5 to the right-hand side. So 25 over 5 plus 8 over 5 is equal to 5b. So b is going to be 33 over 25. So what's our y sub p? It is ax plus b. Now we know what our a and our b are, so it's going to be 2/5 x plus 33 over 25. So what's our general solution? So it's going to be complementary plus particular. Our complementary is up here, so I'm just going to copy paste that. And then our particular is this. So that plus that. Remember that like you need the C1 and C2 for your complementary solution, but you don't need any like C's or anything like that for your particular solution. You're just looking for a single particular solution. Okay. All right, let's move on to 3. Consider this differential equation. Find the complementary solution. Find a particular solution. I basically gave like a couple hints in this one, so I'm basically telling you that you should use variation of parameters. If I didn't tell you this, like you should still kind of know that you need to do variation of parameters though, because you can't make y sub p equal to like a times like e to the x over x squared plus 1 or anything like that. Like it's just not gonna work out. So variation of parameters is kind of the only thing that we can do on this one. And then we'll state the general solution at the end. So complementary, again, convert lambda squared minus 2 lambda plus 1. So this is converting this into a polynomial. Remember that when you have like a y there, that just becomes like a constant. It's not like plus lambda or something like that. This is like another common thing on the quiz. Let me just like take like a go on a tangent real quick. So like if I had like y double prime plus like 5y is equal to 0 or something like that, and if I wanted to solve that, a lot of people like on the quiz would write this as like lambda squared plus like 5 lambda is equal to 0. This is wrong because whenever you have like the y right there, that should translate into like the constant term. So it should really be like just plus 5. So lambda squared plus 5 is equal to 0. Now if this were like y double prime plus 5 y prime, then this would be correct. But without the y prime, if there's no y prime, there should be no lambda over there. All right, back to this problem. So we converted this to the characteristic polynomial. So then this one we can just factor it as lambda minus 1 squared. And so lambda is equal to 1 with multiplicity 2. Cool. So then y sub c is equal to c1 times e to the x, or e to the 1x if you want that, plus c2 times, so whenever you have like multiplicity 2, it should be like x e to the x. So you just like multiply that by the power of x. All right. Let's find a particular solution to the differential equation using variation of parameters. So now we have our y1 and our y2. E to the x will be our y1, and then x e to the x will be our y2. So let's compute our Wronskian. So we get e to the x, and then x e to the x, and then compute derivatives of those. Derivative of e to the x is just e to the x. Derivative of x e to the x. This is another thing that a lot of people messed up last semester, was they forgot to do the product rule on this. Derivative of x times e to the x is going to be the derivative of x, which is 1 times e to the x, and then plus x times the derivative of e to the x. All right, now we'll do e to the x times e to the x plus x e to the x. Remember, e to the x times e to the x is e to the 2x. So this becomes e to the 2x plus x e to the 2x, and then minus this times this. So it's going to be x e to the 2x. The x e to the 2x's cancel, and we're left with e to the 2x. W1, I replace column 1 with our answer column. Notice that this is already normalized for you. If there was like a 5 in front of the y double prime, we would have to divide everything out by a 5 just to normalize it, but it's already normalized for you, so we'll just go right ahead and put our answer column in. So this is our f of x, and then we'll do 0, and then our f of x for our answer column. And then keep column 2 the same. And then we'll do the determinant is going to be this times this, which is just 0, and then minus this times this. So we'll get negative x e to the 2x over x squared plus 1. W2 is going to be e to the x and e to the x. And then replace column 2 with our answer column. So e to the x, x squared plus 1. So we'll get e to the x times e to the x over x squared plus 1, and then like minus 0. I won't bother writing that. So this is just going to be our W2. Probably writing too big. I feel like I'm going to run out of space, but it's fine. All right, U1 is going to be the integral of W1 over W. W1 is this right here, and then divide out by W. That's going to like, we're going to have this e to the 2x divided by e to the 2x right here, so the e to the 2x's are just going to cancel. So we'll get negative x over x squared plus 1, and I'm just running out of space, so I just don't want to write out the steps of e to the 2x over e to the 2x is equal to 1, all that good stuff, but they cancel, right? And then what's this equal to? Well, how do I integrate this? Well, we can do a u sub. So we can do u is equal to x squared plus 1, and then du is equal to 2x dx. So divide through by a 2. We get 1/2 du is equal to x dx. And so I can pull out a negative 1/2 from everything, and I'm left with 1 over u du, which is equal to negative 1 over 2 ln of of u, and what was u? X squared plus 1. All right, so that's our u1. What's our u2? It's w2 over w. And that is equal to, okay, here's our w2. Divide out by w. Again, the e to the 2x is just going to cancel. And we get 1 over x squared plus 1 dx. And here, you should probably know this one, honestly. But I decided to just be nice and remind people in the exam that the integral of 1 over x squared plus 1 is just arctan. So this is arctan of x, and so that's our u2. So what's our particular solution? I'll just write it down here because I'm out of space. So y sub p is equal to u1 y1 plus u2 y2, right? u1 y1 plus u2 y2, and then subbing all the right stuff in. u1 is negative a half ln of x squared plus 1. y1 was e to the x. Remember, this is our y1, this is our y2. All that stuff up here. And then plus u2 y2, arctan of x times y2, which was x e to the x. And then general solution, it's going to be complementary plus particular. So it's going to be, this is our complementary. I'll copy and paste that. And then plus particular, I will copy and paste that. Boom. That is our solution. So we're on an isolated island of dogs that has some initial population of 100 dogs, and the island can only support a population of up to 1,000 dogs. It is observed that after 14 days, there are 150 dogs on the island. We want to find a formula for the number of dogs after t days. All right, so let's look at the formula sheet that's on here. So, so the things that I gave you on the exam were, so this stuff right here is like your variation of parameters stuff. So we just did that one. I just kind of have these ones memorized. Should probably have. I had a request for putting the this one on the exam last semester because some people actually just don't remember it, which is fine. Let's see, this one right here is this one right here, this is your reduction of order formula, which we'll get to one of those problems in a bit. And then this right here is like the formula, just because like these problems, the logistic model problems are very long to like come up with these formulas. I just decided to throw that formula on the formula sheet. So here they are. So this is a formula for your population given the differential equation. By the way, what's the differential equation? It's, okay, I guess we're using capital D for our dog population. So D, rate of change of dogs with respect to time is proportional to the number of dogs present times, so our maximum population is 1,000. So the number of dogs not there would be like 1,000 minus D. All right, so we'll use all this. So then what's so this is going to be our C value, right? So let's find our C value first so that we can throw it into this. So C is going to be our initial population. P0 is your initial population, which is 100. Our M value, that's our maximum population, that's 1,000, minus your initial population. So this is 100 over 900, which is just 1 over 9. So what's our population? It's equal to m times c. M again is 1,000. C is 1 over 9. And this is over c plus e to the negative mkt. And m is 1,000. So 1,000 kt. I kind of like to, whenever this is a fraction that I can clear out, I like to clear out that fraction so I don't have fractions of fractions. So I'll multiply by 9 over 9 to simplify this. So P is equal to 1,000 over 1 plus 9e to the negative 1,000 kt. That's our formula. But we also need to solve for k, right? Oh, sorry, I should be using d's instead of p's. D. There we go. Right, so we know that d of 14 is equal to 150. So let's plug that information in here. So if I plug in 14 to this, that should be equal to 150. And so now I'll just like cross multiply and stuff. So I'll get 1 plus 9e to the 14 times 1,000 is negative 14,000 k. And then we get 1,000 over 150. So I'm just like multiplying this over here and then dividing this over here. Let's see, you can do that. And then we can subtract 1 on both sides. So we get 9e to the negative 14,000 k is equal to, let's see. So this becomes like 100 over 15 minus 15 over 15, which is 85 over 15. And then divide by a 9, and I get 85 over 9 times 15, which is 135. And then we can take ln of both sides. We get negative 14,000 k is equal to ln of 85 over 135. So k is negative 1 over 14,000 times ln of 85 over 135. And so d of t is going to be 1,000 over 1 plus 9e to the, let's see, negative 1,000 times k, which is 1 over negative 14,000 ln of 85 over 135 times t. Let's see, we could simplify this a lot. If you wanted to stop here, that would be fine. I'm going to cancel out the negatives, cancel out the thousands. So this is like just 1 over 14 times t. So it's like t over 14. And so e to the ln. So I'm going to bring the t over 14 as an exponent to the 85 over 135, and then e to the ln of that just cancels. So this is 85 over 135 to the t over 14. All right, and so this is a pretty good formula here. You could simplify that if you wanted to. What's that? 17 over 27. Anyway, I think I'm happy with this. Again, I apologize that I'm like kind of like sniffling a lot. The cold has been like pretty bad for the past couple days, and I'm traveling tomorrow, so I kind of wanted to just get this video done and out there before, because I can't record this on Tuesday, and so if I wanted to record it not sick, I wouldn't be able to do it until like Wednesday. So I just kind of wanted to get this out there as soon as I could. Anyway. Let's move on. We got a reduction of order problem over here. So reduction of order, our formula, that's also on the first page. So this one is just kind of given to you. I think probably telling you to use reduction of order is probably like a little too generous, and I'm not sure that I will do that on future exams. So, okay. I think I would have to on this one. So on this one right here, so if I didn't tell you specifically to use reduction of order, then this would be like lambda squared minus 6 lambda plus 9 is equal to 0 to get your characteristic equation. That's your characteristic equation. Factor that as lambda minus 3 squared is equal to 0, so lambda is equal to 3 with multiplicity 2. So you would already know that your solution should be c1 e to the 3x plus c2 x e to the 3x. So your other solution should be just x e to the 3x, right? So we should just like know this just from like this short little workup here. But I'm specifying that you have to use reduction of order. What I would do in the future is one of two things. I would either, if it's something like this where you could just like do the whole characteristic equation thing, then I would specify use reduction of order. Or if it's like something a little bit more complicated, and like you're not able to find the solutions in this way, and really you don't have any way of finding the solutions, I might just say, given that y1 is equal to something, find a second solution, or find the general solution. The point of what I'm saying is that reduction of order, the whole point of the reduction of order formula is that if you know one solution to your function already, then you can use reduction of order to find a second solution to your differential equation. I think I said that wrong, but if you have one solution to your DE, then you can use this formula to find a second solution to your DE. All right, so anyway, let's just apply the formula, because once you know that you have to use reduction of order, all you have to really do is plug it into the formula, which is kind of why I don't like this problem that much. It's just throw it into a formula, right? So y1 is just e to the 3x, and then this is e to the negative, okay, and what's our p of x? P of x is a negative 6 here. This has to be normalized, so if this wasn't normalized, then you would have to normalize that first. So our p of x is negative 6. Note that it has to be negative 6 because it's just whatever is, attached to that y prime. And then over y1 squared, which is e to the 3x. All right, now we just have to simplify this. So this is e to the 6x over e to the 6x. Right, e to the 3x times e to the 3x is e to the 3x plus 3x, or just e to the 6x. So these cancel. We're left with e to the 3x times the integral of 1, which is just x. So our general solution is c1 y1, which is e to the 3x, plus c2 y2, which is x e to the 3x. So if I didn't specify the reduction of order for this one specifically, you would have been able to do that like already before, but yeah, anyway. All right, so that's it for that exam. So again, there were like a couple areas where I thought like I made the exam a little bit too easy, which resulted in the average just being like unusually high. Like I think it was like high 80 or something like that last semester. So don't expect it to be like quite this level. Maybe expect it to be like somewhere between that level and the level of like the practice exam that's over here, because this one's like a little bit harder. But also you should be like kind of looking at some of the harder examples that appear in like the guided notes and stuff like that. Like I'm not gonna like test you on stuff that like isn't outside of what we've covered in class, or like the WebAssign and stuff like that, right? So for the rest of the video, I'm just going to kind of go through the practice exam, not doing every single problem, but just talking about them, and then maybe if there's like a problem or two that like is different enough from the fall exam, maybe I'll actually do it in detail. But for the most part, I'm just going to talk about them generally. Like this one right here, this is like almost exactly the same as like the dog problem, so we're just going to basically skip this. But so this one right here, you have like 5 students come back to campus over after break with the virus. The campus is isolated with 20,000 students. The rate at which the virus spreads is proportional not only to the number P of infected students, but also to the number of students not infected. So that right there is telling you like dp dt is kp times 20,000 minus p. So it's a logistic model problem. And so again, just like the dog problem, you can just use those formulas to get your population function, p equals blah. But then this problem is like strictly longer than the dog problem, because it says like, well, how many students are going to be infected after 4 days? But I mean, like all I have to do for that is plug in 14. And how many days does it take for the number of infected students to reach 1,000? Well, once you get your population function, you solve the equation P of t equals 1,000. Just find your value of t that gives you that, right? So I probably wouldn't ask you to do these 2 things on the exam, but it's good practice, right? So I threw it on the practice exam anyway. Okay. A tank is filled with, and the reason I wouldn't likely put these on an exam is not because it's hard and you shouldn't be able to do it, but just because it's time consuming, right? We only have 75 minutes for the exam, and this just takes a while if you can get the population function. This stuff is kind of just like Calc 1 or college algebra level stuff. Here we have a mixing problem. Let's actually do the mixing problem. Love mixing problems. All right, so tank is filled with 50 gallons of pure water. Water with 2 pounds of salt per gallon is being poured into the tank at a rate of 5 gallons per minute. Then the well mixed solution is pumped out at a rate of 4 gallons per minute. I think this sentence right here was actually missing from the practice exam when I first posted it. There's an updated version that's posted right now, obviously. Find the number A of t of pounds of salt in the tank at time t. Or I probably should have said find a formula for the number of pounds. But anyway, so we start off by setting up a differential equation. So dA dt, and this is because we're like pumping salt in and then pumping salt out, we're going to say it's going to be the rate at which salt is entering minus the rate at which salt is leaving or being pumped out. Okay, so got our little tank over here, and then let's see, we're pumping in some salt, and then we're mixing it, and then we're pumping out some salt, right? So what's the rate at which salt is entering? So we have a mixture of 2 pounds per gallon, which is being poured into the tank at a rate of 5 gallons per minute. And I'm being very clear with my units here. Oh, oops. So that I can kind of see that, you know, the units of gallons are going to cancel out there, and we're going to be left with 2 times 5, which is 10 pounds of salt per minute. So that's how fast the level of salt is coming into the tank. What's the rate at which salt is leaving the tank? So we have some, so it's going to be like how many like pounds per gallon times how many gallons per minute, right? Well, how many gallons per minute? Well, it's being pumped out at a rate of 4 gallons per minute. So that's the rate at which it's being pumped out. But like, what's the salinity? What's like the concentration of salt? Pounds of salt. How many pounds of salt per gallon? Well, A is literally how many pounds of salt are in the tank at time t. So you have a pounds at time t divided by, well, how many gallons do you have? Well, you start with 50 gallons, right? So you start with 50, and then each minute you're pumping in 5 gallons. So after t minutes, it's going up by 5t gallons, but you're also pumping out 4 gallons per minute. So it goes up by 5t and down by 4t for a total of just 1t. So this is, oh yeah, and this is like in gallons, right? Gallons. So our gallons can cancel, and we get 4a over 50 plus t. That should be pounds per minute. Okay. All right. So what's our differential equation? dA dt is equal to R in, which is 10, minus R out, which is 4a over 50 plus t. Now we just have to solve this differential equation. Okay, so how do I solve this differential equation? Well, this is, you could either recognize this as being linear, or I think it might also be separable if I remember correctly, but I think this problem is probably easier done treating it as a linear differential equation, so that's what I'm going to do. So I'm going to add this to the left-hand side, and I'm going to get dA dt plus, this is really 4 over 50 plus t times a. This is equal to 10. And I'm writing it like this so that I can say, like, oh, I have like a prime plus like something times a, and then is equal to like something, right? So this is clearly linear in this case. So I can just do the, this is also normalized, right? There's nothing in front of dA dt. So I can just do the integrating factor method. So find mu of t, my integrating factor, that's going to be e to the integral of, whatever is attached to the a right here, which is 4 over 50 plus t. Note that it's positive in this case, positive 4 over 50 plus t. So this is e to the 4 ln of absolute value of 50 plus t. You could do a u sub on that one if you aren't like immediately seeing why that is true. And then you could do some log rules. This is like e to the ln of 50 plus t to the fourth, and I can drop the absolute values because anything to the fourth power is going to be positive anyway. So this is 50 plus t to the fourth, because e to the ln of something is just that same something. So we have our integrating factor. We multiply both sides of our differential equation by that integrating factor. So we get 50 plus t to the fourth times dA dt plus 4 times 50 plus t to the fourth divided by 50 plus t. So that would really be to the third. And then times a. And then multiplying on the right side as well, we get 10 times 50 plus t to the fourth. So the left side should, we should then notice that that is equal to the derivative of our integrating factor times a. And we should always check this. If I do the derivative of a, I just get dA dt. And if I do the derivative of 50 plus t to the fourth, I get 4 times 50 plus t to the third times the derivative of 50 plus t, which is just 1. So we are reversing the product rule, and then we get just 10 times 50 plus t to the fourth on the right. And now we can just integrate both sides with respect to t. Derivative, the integral of the derivative just gets you back to where you started. And then on the right hand side, you could do like a u sub here, like u is equal to 50 plus t, and then your du would just be equal to dt, so you get like u to the fourth. Or you could just kind of notice that this is equal to
You just integrate that and get 50 plus t to the fifth divided by 5. 10 over 5 is 2. And then plus c. So then dividing by 50 plus t to the fourth, I get 2 times 50 plus t to the first power, right? I have to the fifth power divided by the fourth power, which is to the first power, and then plus c times 50 plus t to the negative 4. You could write it as c divided by 50 plus t to the fourth. I'm just running out of space, so I'm going to write it like that. Okay. We are not done because we don't know what this c value is right here. So let's go back up here. We need an initial condition. And that's this first sentence right here that we haven't used at all yet. This says the tank is filled with 50 gallons of pure water. I guess we've kind of used it, right? We used the 50 to come up with like this thing over here. But the fact that it's pure water, we haven't used that yet. The fact that it's pure water tells us there's no salt in it at time 0. So A of 0 is equal to 0. If it said that like it's filled with 50 gallons of water with like 10 grams of salt or 10 pounds of salt at the beginning, then that would tell you like A of 0 is equal to 10. If it like was initially filled with 20 pounds of salt, then A of 0 is equal to 20, right? Just like that. So A of 0 is equal to 0 in this case though, so we're just going to plug that stuff in. A of 0 equals 0. So we get 0 is equal to 2 times 50 plus 0 plus c times 50 plus 0 to the negative fourth. And then we can solve for c. Let's see. So I can subtract 2 times 50 on both sides. That's just 100, right? And this is like c over 50 to the fourth. So c is equal to negative 100 times 50 to the fourth. So our function for a is 2 times 50 plus t plus c, which is minus 100 times 50 to the fourth times 50 plus t to the negative 4. That would be our solution. Cool. All right. Let's see. This one's kind of different too. I don't know if we're going to do it in all of its detail, but let's talk about it. All right, so the rate at which the temperature of the body changes is proportional to the difference between the temperature of the body and the temperature of its surroundings. When a steak is removed from a pan, its temperature is measured at 135 degrees Fahrenheit. 5 minutes later, its temperature is 100 degrees. If the temperature of the room is 70 degrees, how long will it take the steak to cool to 85 degrees? I probably, if I were to give you a question like this on the exam, I probably wouldn't actually phrase it like this. I would probably phrase it closer to what you saw on the quiz when we had this type of problem, where it's like, set up the differential equation and then show how to solve that differential equation. And then once you solve that differential equation, then use your like initial conditions or whatever to get an exact answer for the function. Because this as written, this is technically a Calc 1 problem. Like I literally give this problem in my Calc 1 class. So I'm more interested in your ability to do the differential equations part of this problem, right? So that's why I would phrase it in the specific way that's like on the was on the quiz. If I were to phrase it like that, here's what we would do. So we would use this differential equation up here, or this information to set up a differential equation. So the rate at which the temperature, capital T, is changing with respect to time is proportional, so there's going to be K times something, to the difference between the temperature of the body, which is capital T, and the temperature of its surroundings. So the temperature of the surroundings here is just 70 degrees, so I'll just write 70 here. You could write like T sub S for like a placeholder variable and then throw that back in later. Doesn't really matter. you can then divide, so this is separable, right? So I can divide like t minus 70 on both sides. So I get 1 over t minus 70, and then multiply by d little t. And then we can just integrate both sides. So we get ln of t minus 70 is equal to k t plus c, and do e to the power of both sides. We get t minus 70 is equal to c e to the kt. Notice that I'm like dropping the absolute values here because I could do like a plus minus gets absorbed in like this c over here, and remember the c, we're like bring it down. I'm like skipping some steps here that I explained in more detail like in class and stuff like that, but this is kind of what we get. And so t is equal to 70 plus c e to the kt. And then you could just kind of use your initial conditions to figure out what c and k are in that case. But that's kind of just like sort of algebra stuff. So this right here is like the stuff that I'm like most interested in you being able to do. Like this, so like this is probably going to make up like the bulk of the points that you get on like these types of problems. Now, if you were to see a problem phrased exactly like this, and you didn't put like any of this stuff here, like if this was all missing and you just had this one, because of the way that this is phrased, I wouldn't really care, right? Like it's dependent on like how I phrase the question. But if I say like set up the differential equation and then show how to solve the differential equation, that's like when like you actually kind of need these steps, and I'm more likely to kind of ask you to do that sort of thing on an exam. Because I mean, this is a differential equations class. You should know how to set up and solve the differential equation. The whole point of this. Okay. Anyway, I'm posting solutions to these on Husky CT. So if you're interested in like what the algebra there looks like, take a look at that. I'm going to skip it and just talk about the rest of the stuff here. Verify that this set forms a fundamental set for a differential equation. To verify that something forms a fundamental set, there's two things that you have to check. You have to check one, that both of them satisfy the differential equation, and then two, you have to show that the Wronskian is non-zero. This shows that they are linearly independent. Right, so showing that the Wronskian is non-zero, I'll skip that because we already did one of those kind of problems in the beginning. Showing that they satisfy the differential equation, maybe let's just do it for one. Let's just do it for like y1 equals like e to the negative 3x. You know, on an exam you would have to do it for both of them, right? But just take a look at I'll have like the y1 and y2 written out on these solutions that I post in Husky CT. Anyway, to plug it into the DE, you take your first and second derivatives and then plug it in. So our left-hand side is equal to y double prime plus 4 times y prime plus 3 times y. And so this becomes, so I could factor out an e to the negative 3x from everything. I get 9 minus 12 plus 3. That's 0, so this whole thing is equal to 0. And that's what our right-hand side of the differential equation is. So it satisfies a differential equation, right? Been doing this stuff all since day 1, I think, maybe day 2. So yeah, you do it for y1, you do it for y2, and then you compute the Wronskian. Same old, same old. Let's see. This one, very similar to what we did above. I'll just kind of skip that one altogether because there's very little difference here from like the other thing. The complementary solution. If you have y double prime minus 4y, if we're trying to find the complementary solution, quick little check. Should this be lambda squared minus 4 lambda equals 0, or should it be lambda squared minus 4 equals 0? Which one of those should I solve? this one. It should be lambda squared minus 4 is equal to 0, right? If this was minus 4y prime, then it would be minus 4 lambda, but it's just minus 4 for y, so it would be lambda squared minus 4. So this would tell you that lambda is equal to plus or minus 2, and so your complementary solution would be c1 e to the 2x plus c2 e to the negative 2x in that case. Okay, let's see. Yeah, finding a solution to this differential equation. Easiest way to do this one is probably going to be the guess and check method. Probably you could do variation of parameters, but why would you? When the guess and check method is just like going to be a lot quicker, most likely. Anyway, here we go. All right, so here's a variation of parameters one. This one, okay. I messed this one up when I was writing up my solutions in the beginning. So I'll just kind of point out like the main thing that everyone kind of messes up on these things, and that is forgetting that first step of normalizing the differential equation. So this 9 is in front of that y double prime, so we want to start by dividing out by the 9. So that when we go down here and put like our answer column, instead of like 0 and like 3 secant of x over 3, instead of that being our answer column, it should be like 0 1/3 secant of x over 3 for our answer column. So just make sure that you normalize that one so that your whole variation of parameters thing is not just completely thrown off by that factor of 9. Yeah, here I kind of, I'll also mention, for whatever reason, whenever you're doing variation parameters, I feel like there's always like one of the integrals is going to be like a lot easier, and then the other integral is just, for whatever reason, going to be a lot harder. It's just kind of, from the problems that I worked out, it almost always works out that one of the integrals is like a lot trickier than the other one. They're never like about at the same level for some reason. So in this one, to integrate tangent, I just kind of told you like what that integral is. So if you have a variation of parameters one where like one of the integrals is like something that like the integral of tangent, the integral of secant, something like that, like I'm not afraid to like just give you like what that integral is, right? I probably won't tell you how to do it if it's like a U sub problem or like an integration by parts problem or a partial fractions problem. Like you should know how to do those ones. But something like tangent or secant, I'd probably just tell you. This one's good. Let's just do this one because it's kind of quick. So this should be, it's homogeneous, so we just have to convert this to the characteristic polynomial. Lambda squared plus 2 lambda plus 5 equals 0. So again, lambda equals negative b plus or minus square root of b squared minus 4 times a times c. A is 1 over 2a. So this is negative 2 plus or minus square root of 4 minus 20, which is negative 16. So we get negative 1 plus or minus the square root of, and this is like 4i over 2, so that 4i over 2 is 2i. All right, so then y, it's not yc here because it's already homogeneous. You just say y for your general solution. It's going to be c1 times e to the negative x. Remember, this is your alpha, and then 2 is your beta. And then times cosine of 2x plus c2 e to the negative x sine of 2x. All right, cool, that's that. And then this one's just like another reduction of order 1.
It's another one where you would just be able to do this one just by like, factoring this one out or whatever. But there are problems where it's like, y1 is equal to like x squared, um, and then use reduction of order to find the other one, where like you wouldn't be able to like do the whole factoring trick and whatnot. Um, yeah. So yeah, what else is there to say? I don't know. I think I've kind of covered a lot of bases here. There's probably plenty more that I could say on this stuff, um, but I don't want to. I think that's probably a long enough video, and I don't want to just like go over like every single section in pure rigorous detail. Feel free to send me emails about random questions. Again, I'm gonna have solutions, like fully written out solutions, posted on Husky CT. So if you want to look at things in more detail, look at those. Um, and um, yeah, come to office hours. I have office hours Tuesdays and Thursdays, depending on what time your class is. You might not care about the Thursday office hours, but Tuesday, Thursday from 12:30 to 1:45 are my office hours. I'm also free virtually on Wednesday. If you like, would prefer to do that. Like if the office hour times don't work for you, feel free to just shoot me an email and say, hey, can we meet on WebEx or whatever. Um, yeah, cool. Anyway, that's it for now. Thank you so much for listening. Hope this helped, and I'll see you guys in class. Happy studying.